Hello, it's Keith here, and this is lesson 9 of the YQuest series, and we're going to be looking today at the NES specific code. This game's been ported to a lot of 6502 systems, and we're going to be looking at the NES this time. Now, the NES version was a little bit tricky because of the tilemap. Now, on the NES, we can only write to the tilemap during Vblank, which is when the screen is not being drawn. And so what we actually have to do with this version is we have to use a cache and store our tile changes that we want in that cache, and then those changes have to occur during that Vblank in one big go. So it was a bit of a pain, but that's the nature of this machine. So we're going to be looking at how it works today. So there we go. So yep, that's YQuest, and that's what we'll be looking at today. Okay, let's go over to the code and let's check it out. So here's the code. We're going to go through it all and we're going to discuss each part. The first thing you'll see is we've got some collision masks. Now, we're using the tilemap for all the graphics. We're not currently using hardware sprites. So we're limited to an 8x8 grid. And to make sure that the collision logic is working at the same definition as the visual representation, so that the player doesn't bump into something they don't think they're about to, we're actually reducing the resolution of the collision detection. Now, there will later on be a version of this game that uses hardware sprites, so we'll look forward to that, please. But at the moment, we're just using the tilemap, and the reason for that is that this was built on the Simple series, which only used tilemap graphics. So we've carried that sort of tradition on to this version. So that's what that's for here. We're then defining the size of our screen. The multi-platform code works on all systems, and it needs to know what the size of our screen is. We've got a screen width 256 here, which is to center the screen. We're simulating a 256 by 192 size screen here. ZReg is the 0-page entries that I use for my temporary variables, which mimic Z80 registers. User RAM is the temporary data for the game logic. Now, we're actually defining a cartridge with some extra built-in RAM. The way I'm using the video buffer so that we can only write during Vblank actually uses quite a bit of memory, and the NES as by default doesn't have very much. So we're defining a cartridge mapper 4, which defines an extra 8K of RAM within the cartridge, and that's going to be enough for us to have our game variables and also the video buffer. So that's what we're doing there. So here's our NES cartridge header. As I say, it's basically the same as before. We're just defining that extra mapper so that we've got some more memory there. We've then got some 0-page entries. Vblank is for detecting Vblank. We've had that in the past. VDPCT is a new one. Now we're defining a buffer. You can see it's going to be a memory address 200 here, and it's going to store up to 32 entries, 3 bytes each. Now the first 2 bytes is going to be a VRAM address, and the extra byte is going to be the data to write to that address. Now the CT is the position within that buffer that the next write is going to occur to. So we've got that there. We've also got a sprite buffer, although the game doesn't currently use hardware sprites. Basically, I transplanted the code that handles this buffer from my existing examples as is. I didn't take any extra code out because it didn't add much extra bulk to the code, and I wanted to keep it complete because I'm hoping you may want to borrow this for your own projects if you want. So that's why we've got a sprite buffer, even though the game technically doesn't use sprites at this stage, but it will later on, hopefully. Here's our program start. We're just setting things up here. We're defining our palette here, and we're transferring the palette in native format here. So this is selecting the first palette address, and then we're transferring the 4 entries of the palette. We're just using one set of colors here. You can see that the game's graphics are only really 4 color on the NES. Then turning on the screen here, and we're enabling our interrupt handler, the NMI interrupt handler, which occurs during Vblank, and that's going to transfer our buffer into true VRAM. And that's how we can get the graphics moving nice and quickly without waiting for Vblank every time we want to draw a tile, which would be very, very slow. Next, what we need to do is turn on the extra memory at 6000 to 7 FFF here. Now that's in the cartridge because of that selected mapper, and we're using that for our game variables, remember. You see those just here. So we need that, otherwise our game will not work very well. Okay, next what we're doing is we're transferring our tiles from the cartridge ROM into VRAM. The mapper we're using uses VRAM. That's the way I tend to prefer working with things. It's a lot easier, I find, to be able to use VRAM rather than ROM, although by default the NES did use ROM, so it's just something I do in my tutorials. Here we're clearing the game's temporary variables. Here we're starting up the new game, giving the player the lives and resetting the player, turning off the sound, things like that. And next what we're doing here is we're drawing the title screen. Now all graphics, text and also sprites and the title screen are all done with this show sprite routine and various derivatives of it, and that's going to be handling for us the tile map problems. So essentially all we're doing here is we're pointing to our title pick, which is common to all systems, reading in a byte, checking if it's non-zero, and if it is, we're calculating the position within the tile map and then showing the sprite to the screen here. We're repeating until that's done. Here we're showing bits of text. You can see there's a high score and a learnasm.net message there. That's what those are. Here is the start of our new level, or the start of the first level even. And wait for fire. We'll just wait for the player to press fire, clear the screen, center the player again, and initialize the entries for the level. Now here we've got a loop, and this is a delay and also reading the controls here. So any key presses are going to be stored in X here. And read control jewels, which we'll see later, is reading in the joystick directions and fire buttons, and any changes will be stored in X. Now when we get to here, we're going to start drawing things. First we're drawing the UI, that's the score and the lives and all the things in the corners of the screen. We're then going to clear the player sprite. Now we point 0 page entry IX to the player object here, and then use this blank sprite, which will read in the X and Y position to blank out, and we'll see that later as well. Here we've got something called key timeout. Now the game works by acceleration, so if I press up and then release it, I will keep moving in that constant direction. But if I hold up, I'll get faster and faster. But we don't want to get fast too quickly, so until the timeout occurs, we ignore if the buttons are being held down. Now here's the direction processing here, you can see them here. And each one is affecting an acceleration, either Y acceleration or X acceleration. Now these both use IX, which is still pointing to the player object here. And we've got dec IX offset by Y and dinc IX offset by Y, which will change the accelerations accordingly. If the player presses fire 1, we're going to fire a bullet. If the player presses fire 2, we stop the acceleration, so that's like an immediate handbrake kind of thing. So that's quite handy as well. Now when we get down to here, we're saving the new timeout, and we're then drawing all of the in-game objects and calculating the level changes and collision detections, things like that. And then we're looping all the way back up to the top here. This is effectively the infinite loop. Now this is the common code, and this is the platform specific code because of the differences in the fire buttons and direction buttons on some systems. Now clearing the screen is just simply setting the tiles all to 0 here, so that's very straightforward. Print chart also uses the sprites, the tiles. Now the first 96 are characters, the first character being space, there's no characters below 32, so we have to subtract 32, and we load the X and Y position into X and Y here, and then use show sprite to show the character to the screen. Now blank sprite will only work if the collision program is less than 250. Collision program 255 is a uninitialized object, 254 is a dead object, so that's why we're doing that. Do blank here will set the sprite to sprite 0, which is the space character from the font, which will clear it off the screen. Get sprite address here is calculating a animated sprite. Now the first 96 characters are the font, so we add 96. We then load our sprite frame and multiply by 16, because there's 16 sprites in our game sprites, but there's 4 banks, so a total of 64 there. So that's what we're doing there to calculate the final sprite address there within the tile map, within the tile pattern definitions. Do get sprite object will get the X and Y position from the IX register pair in the 0 page, and also the sprite number from the IX there. So that's just getting everything, and that's used for most of the graphics in the game, but pretty much everything except the font, to be honest. All of it's in the same object format. Show sprite here is using get VDP screen pos. Now what this actually does is it calculates a position in the buffer, and it also checks if there's a spare slot in the buffer. We'll see that in a moment. If the buffer's full, it will clear it, you see, and it will return Y pointing to the next position, and then we just store the byte that we want to write to the screen into this position. The tile map position will also be calculated from X and Y here, and that will be stored automatically into the VDP buffer. We'll see that in a moment. Once we've done that though, we need to store the new Y back to CT here, because this function actually zeros the CT. The reason for that is if the Vblank occurred while partial data had been written, it could cause screen corruption. We don't want that. So that's what we're doing there. So get VDP screen pos here is this new modified version. It's not quite the same as the one that was in the simple series. It now uses this buffer. So it's calculating the destination memory address in the same way as it did before. Tilemap's 32 wide, 1 byte per tile. So it's calculating that up. And then what we're doing here is we're getting the current VDP buffer CT, which is the pointer within the buffer. Now we'll just have a look at that now. What it's doing is it's checking if the buffer's full, and if it's not, then it's setting the current pointer to 0 so that if the Vblank occurred, it wouldn't run a partially written list. And it then returns Y as the VDP CT, which is the position within the buffer for the next bytes to be written. Now you can see here that when this has been done, this get VDP screen pos is writing the new destination memory address that it's calculated from the tile position into that buffer, leaving just the final byte for that new tile to be written, and that's what happens just here. So there we go. It's a little bit tricky, but as I say, basically it's a relatively simple format. 3 bytes per buffer entry, high address, low address, and byte to be written at that address, 3 bytes. Now there's some clever ones I've seen online that use RLE compression and things. I haven't done that here. It felt more complicated than beneficial. One thing I should point out, you can change the size of this potentially if you wanted a bigger buffer, but it can't be much bigger. You can't fill the entire screen in Vblank, not unless you can write some very fast code, because it was too slow in my experience. You can't take too long in Vblank, otherwise everything's going to go quite horribly wrong. So I'm only writing 32 tiles per Vblank in this example code. Define tiles here is transferring the bitmap data into VRAM here. We've got to prepare VRAM here, and we've got the transfer routine here, which is basically a loop. We've seen this before in the simple series. Disable and enable screen is for turning off and on the screen, because the alternative for waiting to Vblank is to turn the screen off while we're sending our pattern data. Possibly a better way of doing things. Prepare VRAM is selecting the high-low address, and it does that by writing both bytes of the address to 2006 here. Wait frame will wait for Vblank. We do still need this. We are using it here for when the buffer is full. So we do still have that, even though our code is now working with this interrupt handler transferring the data for us. Here is that interrupt handler. So I've called NMI handler, non-maskable interrupt handler. And what it's doing is it's calculating first the address of the Sprite buffer divided by 256, and it's using a DMA to transfer that straight to the OAM, which is the Sprite definitions. As I say, this game doesn't actually need it, but I thought I'd leave it in because it's a nice bit of code. And then what we're doing here is we're checking if there's any bytes to write, and if there are, we're loading the address in and then writing the data, and we're repeating until we've done all of the bytes in that buffer using VDP-CT. Once we're done, we zero the VDP-CT, and then we zero the scroll position, because remember, any writes to VRAM will mess the scroll position up, which is part of the reason we have to do it in Vblank. We then update Vblank as before, and then we return. That's really all there is to it. So that's doing the entire buffer transfer routine. It's got to be as simple as possible because of the speed. So that's how I've done it there. That's the best I could manage. Maybe there's better ways, but I do not know them. Wait for fire is waiting for the fire button to be pressed and released. This is for the end of the game, game over messages, next level messages, that kind of thing. Read controls dual is reading in from the joysticks. We have to basically strobe the joysticks here, and then we have to read in 1 bit at a time from port 4016 for the joystick here, and then we read in, and each bit will come out in this order, one of the directions, and we're just building them all up into A and ZH here. And when we return, we will have these in that register so we can use them. Here's our bitmap data. These are basically our tile patterns. So we've got the font here, and we've got the 4 banks of frame animation here. We've got our palette here for just 4 colors here in reverse order, just for convenience, so that I could use the X register for 2 purposes basically, and when it reached 0. And then here we've got some common code, and finally we've got our cartridge footer here. Now this is quite important here. We've got our non-maskable interrupt handler, which points to this here, and that's what defines it as being the code that's going to be running during Vblank. So we've got our program start here, which is just the main piece of code. Now IRQ handler we don't actually need, so that's just returning straight away. Of course, there is one other thing that we did need to do to get our interrupt handler working, and that is turn it on just here. So it's not just this code at the end that does it, there's the other bit as well. But that's about all there is to it. It's not too bad. As I say, the getting the in NMI to handle updating the buffer was a little bit of a pain, but it's not too bad relatively speaking, and it solves the problems before of waiting for Vblank every tile, right, which really was not viable for a game like this on the NES. So there we go. Well, I hope you found this interesting. If you have, please like and subscribe. Liking the videos helps because it encourages YouTube to suggest them to the people, and subscribing helps keep my morale up and keeps me working on all these projects. We're going to be coming back to this later on. I've started making versions that use hardware sprites to one extent or another, so hopefully we'll have a version with a bit smoother movement later on, but not quite yet. It'll be coming down the road, so please hang around for that. But anyway, I hope you found this interesting. If you have, go and get the source code from the website, and as I always say, you're welcome to use any parts of it in any way that benefits you. You don't need to give me credit or anything, I don't care. So take care, have a lot of fun, thanks for watching, and goodbye.